Good morning. Welcome to this keynote speech section by Shuchi I am Kong from the Education University of Hong Kong. I am delighted to introduce the speaker of this keynote speech section, Dr. Shuchi Grover. Dr. Grover is the research scientist specialized in computer science education at Affinity in the United States. With the solid educational background in computer science and learning science at Stanford University and Harvard University, Dr. Grover is renowned for her research on computational thinking, computer science education, and STEM plus computing integration in K-12. Dr. Grover is actively committed to national initiative to bring rich computing experiences to school children. She is the advisor to the National K-12 Computer Science Framework in the United States and the advisor to K-12 school districts on computer science implementation and integration. Dr. Grover is also actively involved in global research communities related to her academic expertise. She is a member of ACM Education Council, a member of the Computer Science Teachers Association's Task Force on Computational Thinking, and a member of the editorial board of ACM Transactions on Computer Education. In this keynote speech, Dr. Grover is going to first share her reflective remarks of computational thinking and then discuss the directions and ways to apply learning theory into computer science curricula for fostering the next generation to develop computational thinking. May I invite you to join me to welcome Dr. Grover for the keynote speech. Dr. Grover, please.
Thank you, Suchong. Professor Kong, I should say, and thank you, Didit, and Longxiang, and other organizers of ICCE 2018 for this invitation and honor. Is everything all right? I am really delighted to be here. Can everybody hear me all right? I think this is better. So I'm really delighted to be here in Manila for the first time. I'd like to begin by sharing a very small personal connection with this date and ICCE. So this is an image on this very day 2 years ago, 29th November 2016. I took this selfie with my father as I was headed to ICCE 2016 in Mumbai. I had gone from the US to India a few days early, spent some time at home, and I was about to board the flight to Mumbai. And this ended up being my last few moments with my father, who passed away last year. So it feels really good to be marking this day, doing something that would have made him proud. So I think now is also a good time to acknowledge all the collaborators that I work with across several institutions with whom I've had the pleasure to work with on several projects related to computational thinking. And of course, they've all shaped my thinking on various aspects of this topic. And of course, right in the center there, the National Science Foundation, without whose grant support I would not be doing all this research that I do. So let's talk computational thinking. It's been such a huge topic of discussion and excitement and debate and confusion and research, and something I've been thinking about for quite some time. And there are several questions that come up around CT. I'm going to use the phrase, the short form CT for computational thinking. And, I'm sure many of you may have thought about these. By the way, how many of you are familiar with the phrase computational thinking? Okay, most people. So, because I'm not going to go so much into the definitions and the why of CT. I think there's several articles out there that make a very compelling case, many of which I have written. I'm going to focus today more on the what and the where and the how of bringing CT into the classroom. And when I say classroom, I'm talking about K-12 school education. And I should add that, even though I'm going to address most of these, we may not have 100% clarity on all of these right now, this day today. But that's okay. Subjects like mathematics and science and reading have been around for decades, centuries. And you'll still find those folks arguing about things like this, arguing about how things should be, kids should be taught to read, or how they should be taught mathematics. And just the other day, last month, I came across this. Can we settle on what mathematical thinking is? So, compared to disciplines like mathematics and reading, computing is a very young discipline. And, computational thinking and CS being taught in K-12 schools is really in its infancy. So I think we should really be, not be so hard on ourselves for trying to figure this out. So one of the things I've realized as an academic is that it's interesting to sort of reflect and trace your own trajectory and your own relationship to an idea. And I've been doing research on this topic for about 10 years now, and this work, allows me to bring my two disciplines that I've been trained in, computer science and education, together in a wonderful way. But I'm going to give you a quick glimpse of the types of projects that I've been working on so that you know what informs my work. So I've been looking at computational discourse with middle school students working in MIT App Inventor. I've been looking at designing curriculum for introductory computer science, which balances designs for deeper learning. Looking at exploratory activities for computational concepts, for introducing computational concepts in introductory programming. Synergistic learning of physics and computational thinking through computational model building. Integrating CT into science and math activities for the really little ones, pre-K learners, preschool learners in their formal and informal settings. And of course, looking at a few different things like, learning analytics to understand computational thinking processes and practices as students are doing introductory programming activities. This project was based in the context of ALICE. And measuring collaborative computational problem-solving skills, again, using analytics techniques, and then understanding implementation factors in computer science in classrooms. And we'll take a closer look at a few of these projects, not all of them. But really, my introduction to this idea goes back much farther, almost 20 years, and it was very organic. So after I made a career shift from computer science and software engineering into the US, I actually moved to India for a few years. And there I was working as an educational technologist based in Bangalore. And I ran after school and in-school clubs and workshops on robotics and programming. I worked with teachers to integrate programming like in environments like Scratch and Logo into their this list of all these activities people And this blog post actually morphed into a national policy paper for in 2000 and commenced my PhD at Stanford. I ICCE, the International Society for Technology in Education, published this version of the article that now dug deeper into the kinds of skills that kids could be developing through this kind of curriculum. And I focused on algorithmic thinking and Boolean logic and, data structures and using everyday tools like free tools like Alice and Scratch and Microsoft Excel and databases. And the interesting thing in all of this was that nowhere in all of this did I mention the phrase computational thinking, though clearly that was what I was advocating for. And that was simply because I had never read Jeanette Wing. Until then, I was back in India as a practitioner. I was far removed from the world of academic writing, and so I hadn't heard of this phrase, but that was exactly what I was looking at. And so, when I did come across this article that we now see as a seminal work by Jeanette Wing in 2006 called Computational Thinking, I felt like it really articulated all the things that I had been, and very much more compellingly than I did, all the things that I had been advocating for. And so naturally it became the topic of my dissertation and my PhD research at Stanford with Roy P. And here's the paper on computational thinking that many of you may have seen and perhaps cited if you're working in the field of computational thinking. It came out in January 2013, but it was actually my PhD qualifying paper that I had written in 2011 and presented to my committee. And over 2012, I had worked to refine it into a journal paper. And in it, I talked about, I traced all the things that were happening since Jeanette Wing's article on computational thinking, and I sort of broke it down into what I felt at the time were these elements of computational thinking. And it also touched upon some of the issues that we still debate today. Some of those questions that I brought up earlier were mentioned even in that piece. And so a key idea that Jeanette Wing expressed about computational thinking was that it's thinking like a computer scientist. And that's caused a lot of confusion and heartburn for a lot of people. And so I think a good starting point is to actually understand what that means and trace that idea back to its origins. And if you dig deep into computing literature, you'll find that computer scientists have been talking about or mulling on this idea of what computer science thinking is since the 1970s and 80s. In fact, eminent scientists like Donald Knuth have written about computer science thinking over 40 years ago. And so in fact, in a recent blog post that I wrote for communications for the ACM, I proposed a more accurate timeline, and I said we should be acknowledging some of this early writing because that's where the idea of computer science thinking is coming from. It's coming from well before Jeanette Wing. And so Donald Knuth, in a fascinating 1980 paper, which became a journal article in 1985, wonders about what most mathematicians have most mathematicians have an essentially different thinking process from that of most computer scientists? And through a very fascinating analytic technique that I urge you all to check out, he basically comes up with a list for mathematical thinking and computer science thinking. And there, of course, we see a huge overlap. We see, formula manipulation is weak in CS, but representation of reality, reduction to simpler problems, abstract reasoning, information structures, algorithms, pattern recognition, and generalization. These are all the things that he mentioned back then as things that both computer scientists and mathematicians do. But he said there were a few distinctions. Mathematical thinking involved dealing with infinity, which computer science can never do because we are always constrained by the physical constraints of the machine. And conversely, computer scientists deal with complexity. And again, it comes from being physically constrained by the machine that you think about efficiency and cost. And that's where the overlaps with engineering thinking and design thinking lie. And there is, of course, this temporal notion of process in computer science thinking that does not exist in mathematical thinking. So there's this dynamic notion of state that doesn't exist in mathematics. And in fact, back in the 70s, he had written articles on how the assignment of the equal to sign is very different in mathematics than it is in computer science. And of course, I wish people hadn't used the equal to sign operator. If it's assignment, use something else, maybe an arrow or whatever. There's another article that I find very useful for this. It's by Peter Denning. It's called Computer Science, the Discipline. He wrote it in 1997 and refined it in 1999 to be published in the 2000 Encyclopedia of Computer Science. And in that, in addition to all the content topics of CS, he listed these standard concerns of the field and said that every practitioner of the discipline must be skilled in 4 basic areas: algorithmic thinking, representation, programming, and design. And he listed out what we all recognize, as algorithmic thinking, step-by-step procedure, representation, ways in which data should be organized or stored, and inventing new ways of encoding phenomena so that you can allow for algorithmic processing. Programming, which, is about taking these algorithms and representations into a software that can be executed by a computer, so you have to know about programming languages and other things. And he also included these ideas of testing, debugging, and modularity that we sometimes pull out as separate topics of CT. And he talked about design, where he talked about the practical considerations of doing these things, trade-offs, constraints, and reliability. And, these are all the things that we recognize as CT practices. These are the things we've been, talking about these last few years. But they, these ideas go way back. They've been articulated by computer scientists. And CS being articulated as a content area, but also these practices which on problem-solving skills, which include, you know, other things besides programming. To me, this is a very clear answer to the question, is CT the same as programming? Well, CT is more than programming, as we have, many of us have often reiterated. But that said, programming is a very key part of introductory computing curricula, especially for younger students. Coding and programming involves many facets of CT, concepts and practices. It's an important tool to teach and learn and assess CT. There are many fun and engaging environments out there now, block-based programming. Ulrich, even though you have problems with those, it's a good way to introduce kids to programming in the beginning. It can also involve tangibles, robotics, e-textiles, makerspace, that many kids find very uniquely appealing. And artifacts as forms of creative expression, that's a view that Mitch Resnick, advocates for a lot, that it's hugely motivating and gratifying and personally meaningful for students. But students can engage in CT without coding. There's more to CS than coding, and a focus on CT helps with deeper learning of coding. And so, in addition to coding, CT is about students engaging in questions like, is there a pattern between this problem and similar problems we have tackled before? This is your, problem pattern recognition. Can this problem be broken down into sub-problems to tackle it more easily? Can it be better solved by a human or a computer? These are important questions kids should be asking if it is computational thinking, because you want to think about automation and what automation brings to the table. What details are important and what can I ignore for the purposes of creating? That's abstraction. Can I create a general solution? How? What sort of data are involved? How can data best be organized to solve this problem? How can data be represented? And what is the step-by-step procedure that I can articulate? How can I represent it in algorithmic steps? What technology can be applied to the problem? What computational strategies would be useful to solve this? And finally, what are the limitations and trade-offs and constraints of different types of solutions related to solving this problem? So what we're talking about is computational thinking as a disciplinary skill for computer science. And those are the things that Knuth and Denning have written about. And while we think about bringing computer science as a new subject to schools, this is how we could be viewing computational thinking. One way of viewing computational thinking is to basically focus on these problem-solving skills in addition to content. But the what and how of doing all of this is always a challenge, and so we always turn to education research for that. And so thinking skills have been researched for decades in education. But the focus, of course, on higher order thinking skills and disciplinary thinking is something more new, since things have shifted, towards 21st century learning and life and work. And here are some highlights from these reports and research. Thinking skills basically signal a shift from this very rote learning and accumulation of facts to basically ways of doing, more authenticity in subject learning. It increases awareness of the discipline. It's actually synonymous with problem solving. When you read literature on thinking skills, I've always felt computational problem solving would have been maybe a better phrase for computational thinking, but let's not go there. Most disciplinary higher order thinking skills share elements of reasoning and problem solving. And so there are overlaps. So when people say, oh, but this is mathematical thinking and this is design thinking, well, there are overlaps. There are overlaps, in fact, in scientific thinking and thinking like a historian. Both involve very heavy evidence-based reasoning, and mathematical thinking and CT we've already seen. And this involves, disciplinary thinking also involves learning of tools, skills, practices, and vocabulary of the discipline. It's about, sort of developing an affinity for the discipline, becoming part of a community of that discipline. And those things are pretty empowering for students. And new curricular frameworks, at least in the United States, the next generation science standards, the Common Core standards for mathematics and language arts and social studies, they all emphasize disciplinary thinking. I don't know if the same has been happening in other countries. I'm sure it is. And so for science, you have thinking like a scientist. For history, you have thinking like a historian. For mathematics, you have thinking like a mathematician. And therefore, for the computer science classroom, you have thinking like a computer scientist, and that's how you can view computational thinking as a disciplinary skill for those classrooms. Another big idea that has emerged from this work, especially from Education for Life and Work by James Pellegrino and Hilton, and work by the Hewlett Foundation for the last 8 or so years, is this idea of deeper learning. You'll see and hear the phrase a lot, and I use it a lot myself, but it is this idea of, in order for facilitating transfer, you want to aim for deeper learning. And what deeper learning comprises is 3 very intertwined competencies: cognitive, intrapersonal, and interpersonal. And the cognitive earlier used to simply focus on disciplinary mastery with content areas. But now it has expanded to include critical thinking and problem-solving skills of the domain. And so that's the disciplinary thinking part that comes with the content. And that's why you'll find a lot of frameworks looking at concepts and practices. And intrapersonal, of course, a lot of you are looking at things like metacognition and regulation and mindsets and those kinds of things, interpersonal collaboration, communication. All of this is sort of another avatar, so to speak, of this 21st century view of learning. And the computer science framework that we developed in the United States, I was involved in this effort. And how pedagogy and literature on pedagogy on how these deeper thinking skills for transfer. So a few pointed insights. Thinking skills are learned in context, always much better learned in context. If you want to transfer from one context to the next, you have to work for it. Your design has to work in both contexts maybe. And so having a course separately on critical thinking or a separate course called computational thinking doesn't really work too well. You want to embed it in a context of, say, computer science learning or other subject learning. Abstract representations of knowledge help promote transfer. Skills taught in multiple contexts are more likely to promote transfer. This is something that I was talking to Soren about at his talk yesterday. And fostering an expectation that students will continue to use what they learn is also motivating and helps for transfer. This is sort of what Ben was talking about when he talked about Coach Mike, you know, making things more motivating for the learner before they start, you know, their, whatever it is they're learning. Even if there is little transfer, this is what they say, even if there is little transfer beyond context, if you focus on deeper conceptual learning, you will have achieved good learning in that context, and it'll definitely, you know, afford good near transfer, definitely. Here's the negative. Over-contextualizing skills reduces transfer, and this is something we're going to talk about. It's very relevant for computer science tools and programming languages. And one thing that I just want to put out there, I don't want to start a debate or anything, but this is what I think, and I think the literature sort of bears this out. Discovery learning does not work too well for conceptual learning. We heard that yesterday in Soren's talk when he said that for higher abstractions and for more complex stuff, you needed scaffolding. It's been shown over and over, and of course, Kirshner, Sweller, and Clark has been cited 5,000 or 6,000 times for good reason. But exploration and inquiry has a place, and so you need to balance guided inquiry and exploration with instruction, and how to do that is always challenging. It's a challenging design exercise in curriculum design. But usually, in several contexts, inquiry before instruction has been shown to result in better learning. And there's a very good article by Dan Schwartz and John Bransford from 1998 called A Time for Telling that I would recommend. So we've talked a little bit about the what and the how, and learning is always this trifecta of curriculum, pedagogy, and assessment. You always need this feedback loop, and so assessment always needs to be part of the design process. I'm going to talk a little bit about CT assessments today, not a whole lot. But it was this, you know, all these 3 things that I sort of looked at when I worked on this, on my dissertation research to design an introductory programming course, CS course for middle school students. And by the way, that's a working QR code. And CT with a focus, CS with a focus on computational thinking. It was a 7-week introductory curriculum designed mostly online in instructional videos on the Stanford MOOC platform. But it also was an in-class experience, so there was blended in-class learning happening. And the curriculum was designed to provide an awareness of the discipline as a very conscious exercise of the curriculum, to provide perspectives of computing and also look at core disciplinary concepts and practices of CS as CT. And so you see all those elements of deeper learning happening there. And the goal, the mission, was to foster deeper thinking skills rather than simply learning the syntax of the programming environment. And what I was using was Scratch. And that's a very big deal, to actually have this kind of mindset that you're teaching computer science or computational thinking via a programming language or an environment versus teaching the environment or programming, in Scratch. And that shift in the mindset actually does a lot for curriculum design. And I've encouraged teachers to sort of think about it in this way. And this goes back to the idea of over-contextualizing things. If you just teach Scratch, then they're not going broad and deep as they should. And so, perspectives of computing were shared, through this, through motivating short videos. Before they started the lesson everywhere, there's a playlist on YouTube called Computing is Everywhere. And this was an expansively framed curriculum with students watching these videos, much like Coach Mike that Ben talked about. Every topic began with a thought question that connected to something in the real world that the kids might connect to. And from there, it was this exercise of designing a curricular sequence, with certain core learning mechanics that included instructional videos, thought questions and exploration, discussion prompts or Scratch activities, programming, directed and open-ended, formative quizzes with automated feedback and explanations, and then, extension activities if students are moving ahead. And the pedagogical underpinnings came from the learning sciences. And usually the kinds of things that people say help with conceptual understanding, and that includes cognitive apprenticeship, modeling with worked out examples, mediating transfer. It's this idea of students seeing a bigger purpose for what they're learning. It's motivating. Constructionist learning by doing. Of course, they're learning programming, so it's got to have that. Guided inquiry or thought questions before instruction, systems of assessment, multifaceted measurement of student learning, and analogous representations for deeper conceptual learning. That's an idea that I wish more people would do. I talked about multiple representations. An example of this would be that throughout, students saw or worked with code in various forms. They always wrote it out in pseudocode or a flowchart or a storyboard. And then, of course, they would see it in Scratch when they, moved from doing it on paper to the Scratch environment. And sometimes they would see that same solution as a text-based solution in Java or something. And that was just to give students a sense that this is not about those blocks that you've put together. It's about a sequence of steps and algorithm, and it can take various forms, but it is the deeper structure is what you want them to see rather than the surface features. And that's the idea of multiple representations and analogous representations. Systems of assessment, I'm not going to go too deeply. Suffice to say that there were several types of assessments, formative and summative, that were part of this curriculum, open-ended and directed programming assignments, innovative programming exercises like Parsons puzzles, and they would program partially completed code. They would debug a faulty piece of code, and the summative assessment had them doing free choice projects alone or with a partner. They took an assessment test, a post test, which was borrowed from Israel, a national exam. They presented their work. That's all part of the community building and communication around their artifacts, artifact-based interviews. There was a specially designed transfer assessment, preparation for future learning assessment. The phrase preparation for future learning, by the way, I haven't cited it here, but it comes from Dan Schwartz and John Bransford's work that I'll talk How should you sequence it? When should you tell? What should you tell? What should that explanation be? Should it be a worked out example? Should you debug faulty code with the classroom? Should you be talking about alternative solutions? All those things are things that you want to be thinking about. And this particular idea of what kind of guided exploration would be good before they program was something that I found so compelling that we actually did a whole research project on this, on the topics that students found most difficult, variables, expressions, loops, and abstraction at SRI. And here we drew inspiration from mathematics education research. And I'm sorry, I forgot to run my timer, so I have no idea how long I've been talking. It was to help diverse students develop deeper conceptual learning. And I'm going to play a short video, which will give you a sense for the project. We created this for the
states, districts, and schools have.
Can we turn up the audio? Can you all hear it? No one there? No tech support?
Begun to address the need to make computer science accessible for all K-12 students. Most computer science classes focus on coding. When students states, districts, and schools have begun to address the need to make computer science accessible for all K-12 students. Most computer science classes focus on coding. When students rapidly code games, stories, and apps, they're motivated and engaged. But how deeply do they engage with the underlying?
We've developed a suite of digital and unplugged activities for middle schoolers to learn the Vela concepts. These activities help students explore the concepts in interesting ways, and they complement introductory programming experiences in environments like Scratch.
For example, we treat variables and expressions as dynamic quantities, values that can change over time. This helps students distinguish variables in programming from the types of variables they've learned about in math class. We also use comic strip panels as a powerful non-textual metaphor to help students think about sequence and pattern and repetition, first in stories and then later in code. Our activities introduce abstraction as a technique for capturing something complex by giving it a simple name that becomes an operational shorthand for the thing itself, hiding all of its complexity. The activities draw on research in mathematics education, specifically on learning through dynamic representational technologies.
To measure how well students learn these concepts, we develop formative and summative assessments focused on Vela ideas.
We also conducted extensive research in 3 diverse middle school classrooms in San Francisco that implemented the Vela curriculum. The teachers participated in professional development before implementing Vela in their classrooms. We're developing rich case studies from 70 observations and 30 interviews with teachers and students.
Piloting Vela was a great learning experience for me. I really appreciated the clear conceptual focus, which students revisited in the related Scratch lessons.
We thank our team at SRI and our partners at the San Francisco Unified School District.
All right, and since then they have been using it with all their middle school classrooms for the last 2 years, which is about 10,000 students. So a quick idea of how unplugged activities sort of help students. One of the things we found in programming is that students find it very hard to, put together Boolean expressions involving variables. They're very easily, work with simple loops, but when it comes to a non-deterministic loop like a while or a repeat until, so we had kids actually think about what the outcome variable is, what controlling variables are, and these everyday scenarios that we, shared with them. The Boolean operators to be used and the expression. And as we mentioned in the video, we used evidence-centered design to design assessment, which actually gets at their thinking about what the variable is and how they would model, stopping conditions and things like that, pattern recognition and generalization and such. And for the outcome, we looked at free choice projects for our sample and an equal number of students that use the curriculum without the Vela intervention in between. and it was found. And we also had a pre-post test, as we mentioned, and we found that students in all 3 grades had that, you know what that teacher talked about out of her intuition, it did bear out in actual analysis of the projects, that they were much more sophisticated, used advanced constructs, and you know, there were significant pre-post gains for all 3 grades. Learning gains were not significant by grade, gender, or ethnicity, which is something that we really do care about. And in terms of assessment for transfer, I just want to point out the work that this work of Alex Repening that I've always found to be very useful, though I haven't been able to use it very much, around computational thinking patterns with his students, Ashok Basavapatna and Kyohan Ko. But that's just something I want to put out there. So now, shifting gears, let's look at a whole different view of CT, where CT is not about thinking like a computer scientist, or it's not about thinking about computer science at all. It's about using computers and programming as a tool, as a powerful tool for learning in other disciplines. And of course, the father of that view would be Seymour Papert, who talked about programming as the most powerful medium of developing sophisticated and rigorous thinking for mathematics and physics and grammar and statistics. And he believed that programming should be a key part of the intellectual development of people growing up. And his view was also echoed by Andrea de Sessa, who actually gave it a name. He called it computational literacy. And he also, you know, thought of this as a medium, programming as a medium for students to learn new ways of thinking and sense-making in other subjects. And it's interesting, you know, de Sessa finished his PhD at MIT and joined Papert's group, who had a PhD in mathematics. It's interesting that these were people coming not from computer science, like the earlier stuff. These are people coming from outside the discipline who look at the value of these tools for new kinds of learning in their disciplines. And you know, this view is actually crucially important today, because we live in a world of growing computational X. Every day there's a new one cropping up in universities and being taught and practiced. And it's all about using computing and CT to innovate in various fields, from physics to finance. And so there's this desire to integrate computational thinking and maybe just programming to all classrooms, to bring computing to enrich the learning process, sort of in the manner that we integrated technology and the way I talked about long ago in my blog post. So, so we have what we can look at as CT for integration. Now, this is the other kind of view, where we bring CT into a non-CS classroom to foster new ways of sense-making. That's crucial for the 21st century, because, you know, computing is integral to everything that we do. And this idea of 21st century skills, I mean, I feel it can be called the 5th C of 21st century skills. I gave this keynote at Singapore earlier this year. And in this article, I talk about, you know, making, you know, along with communication, collaboration, creativity, and critical thinking, we could be thinking of computational thinking in the same way in order to be able to sort of spread it out across various classrooms and curricula. And so in that article, I had shared various examples. I hadn't tried them, but, you know, various examples of how this could be done in language arts, in mathematics. I'll let you read them. In social studies, and science. And you might notice as you're reading them that they're not all the same. You know, in some the CT looks nice and, you know, deep and transformative. In others, it's unplugged activities where kids are just, you know, sequencing things. So I think it's important to realize that CT can be integrated in a spectrum from low CT to high CT. It's a way that teachers and researchers can use to understand how shallow or deep the integration is, keeping in mind that the goal of CT is to create representations and algorithms in a way that they can be potentially solved by a computer. So, you know, at the low end, you might have something like unplugged activities that are more useful for maybe younger children or kids just getting introduced to computational thinking. And, you know, but these are foundational for them to understand what an algorithm means, what logic is, what pattern recognition means, etc. Then you might have students creating programs, but in a more mechanistic way. They're just putting into a program what they do manually. Like in mathematics, they could be writing an algorithm to solve, you know, a quadratic equation. But then you take it up a notch or two, and you may have students writing programs that are actually helping with sense making. Now they're modeling and interrogating and predicting and trying to, understand a phenomena or a relationship through those programs. And at the highest end, you might have something truly transformative where they may be creating new representations that allow for algorithmic processing by a machine for new interpretations that can only be possible through automation. And, and it's important to, let teachers realize that it doesn't always have to be at this high end all the time. It could be, these various activities could be doing these things over the course of a year or over the course of the K-12 journey. They could be experiencing these in different ways. And I see this as potentially a learning progression for computational thinking. So I'm going to share a couple of examples of the two higher ones there. The first one comes from CT Integration in Language Arts. This article just came out in EdSurge. I had given it to them several days ago. But it's this idea of computational literacy and literary analysis. It's actually a thing now and a bona fide subject being taught in university. And it helps students answer questions like these. I've actually pulled them up from a curriculum in Columbia University. And you can tell that it's using a lot of computational analytic techniques like natural language processing or bag of words or pattern matching and things like that to bear on literary work. But for using CT for a new kind of literary analysis that students can do even in K-12 classrooms, I found this work to be particularly fascinating. It's the work of a Stanford professor called Franco Moretti, who leads a group called Computational Criticism at Stanford. And he basically uses social network analysis or network theory to analyze novels. And so the idea is basically, all the characters in the novel become nodes, and any interaction between them is represented by an edge. And, so it's interesting that just changing a novel into this kind of a representation can truly transform how you look at it. And Moretti published this article on such an analysis for Hamlet, Shakespeare's Hamlet. And the article says, seen through Moretti's network diagrams, Hamlet often seems brand new. One notices, for example, that of all the characters who speak to both Hamlet and Claudius, only 2 managed to survive the play. Moretti calls this part of the network the region of death. The tragedy, he wrote, is all there in this graph. Or one notices that Rosencrantz and Guildenstern, the most famous pair of minor characters in all of Shakespeare, never speak to each other. You can see that there. And he also presented a network of Hamlet without Hamlet. Imagine thinking about what if the main character was not there? What does the story look like? And you find these orphan nodes, or you find people that are now no longer connected because that Hamlet node is missing. And so I found this to be an excellent example of how CT brings a new kind of abstraction and what that new abstraction gives to students, a new way of analyzing the story. But I think this should be extended further. Remember what Denning said. It's about the skill of representation should be about inventing new ways of encoding phenomena to allow for algorithmic processing. So you want students to be asking that question, how can I convert this graph so that I can analyze it computationally? And so you take the next step and have students learn how to transform the graph, which most of you who have exposure to computer science know is to create an adjacency matrix. And every node there then becomes, it's a 2-dimensional array, and wherever there's an edge, you represent it with a 1. And you can think of a weighted graph. This is an unweighted graph, but if you think of a weighted graph where you actually have a number associated with the number of times somebody interacted, then you could be doing a different kind of analysis, strength of relationships and things like that. And, for those who know more computing, if you're thinking weighted graphs, you could be talking about optimal paths and Dijkstra's algorithm. You can extend it in, to become deeply CS in a language arts classroom. And, as we all know, getting your data structures correct first is, very crucial. The rest of the program writes itself. I may be dating myself here, but I learned Pascal as my first language, and that was the textbook. Data structures plus algorithms is programs. So giving students the sense of the importance of data structures and what they could do. But why stop at Hamlet when students could be looking at interesting things like Harry Potter that are so much more contemporary? And it turns out somebody has already created this. On GitHub, I found a social network, an interactive one that students can play with, which basically, shows who everybody is connected to, and this one is for this terribly evil woman. And you can, see maybe who had better role to play, Hermione or Ron, or, who never spoke to Harry Potter in all of the novel. And you could be spending hours on, and kids could find this so fascinating. So to recap, you have an original form of information and a novel, and you use a new abstraction, and it suddenly, the analysis of that abstraction gives you deeper insights and ahas. Or you could convert that abstraction into a data structure that can be used in a program, and then you program it and do some additional analysis. Either way, students are reaching deeper insights and ahas through this. So my last example is going to be from computational modeling in science, and here's a project that at least 3 of us in the room are neck deep in, involved in. It's an exciting project involving learning by modeling in the world of C2 STEM, and it's a large multi-institutional endeavor that's being led by Gautam Biswas of Vanderbilt, and Nicole, his graduate student, has a key part of this project. And all those animations and those pretty graphics, by the way, are Nicole's work. And so middle and high school students here use programming language, the SNAP programming environment, an extension of SNAP, to build scientific models. And we've designed units like this kinematics unit, for example, where they have to, again, set in a real world, give them a real world kind of problem, and they have to take medical aid to, a far to reach place in the Amazon, and so they have to travel by land, water, and air. And the land piece sort of maps to the one-dimensional motion with constant velocity and acceleration, and the river gives you the two-dimensional with the river velocity that has to be taken into account, and of course the drone involves gravity. And like with other designs, we are working with how to sort of integrate instructional tasks, inquiry, model building tasks, embedded formative assessment. And the pedagogical design here is around guided inquiry, constructionism, formative feedback. It's a learning by modeling approach where you want conceptual modeling to precede computational modeling in a domain-specific modeling language. And I'll show you an example of that. And it has embedded formative assessments, summative assessments, all aimed at learning of both physics and computational thinking. And there is this piece where we are trying to see what part of this transfers. And so I'm going to play a brief animation. This is a truck stopping model, and as you'll see, it has steps, blocks like the simulation step, which is a step that's been, provided to students. They can look at various representations of what happened. They can look at it as a graph. They can look at the data as a table, which we found students use often when they're debugging their code. You have blocks like, velocity and things that are relevant to physics. That's the domain-specific language piece. And the embedded assessments, basically, these are things that they do as part of the model building, curriculum. Sometimes you give them partially developed code. Here in this one, again, drawn from a real-life example of how Josh and Kate are going to make it to point C at an airport when Josh hops onto the walkway, whereas Kate does not. And you need to model it and then answer the questions of how much sooner Josh is going to reach point C, or where will Kate be when Josh reaches point C. And so, again, just to give a sense for what this looks like, we've already coded Kate because they've already done constant velocity. They don't need to sort of bother with that. We need them to think about resultant velocity when both the walkway and Josh are moving. And so that's the part that they need to focus on, which is this piece. So they actually need to edit that block and code it for calculating the resultant velocity. So what's happening in this work, we've done studies in several classrooms now with hundreds of students. There's domain-specific learning happening. There's the development of CT skills happening. this honing of programming or learning for the first time. And what's most interesting is this integrated and mutually supportive synergistic learning of both domain and CT. And we could talk more about that, but as it turns out, there is a paper I would highly recommend. You see it's been nominated for Best Overall Paper, Best Student Paper by Nicole Hutchins. It's on 30th November, tomorrow, 2:10 p.m. I would highly recommend that you attend it and learn much more about this wonderful project. So recapping, all the things that we've talked about CT for integration, I want to share findings from another workshop that was funded by the National Science Foundation, in which we looked at several projects where CT integration was happening and how teachers were integrating CT. And what we found, most of the projects came from science, but still, we found that the powerful stuff that CT was helping with was understanding of systems, what we were calling sense-making, innovating with computational representations, engaging in collective sense-making around data, designing solutions that leverage computational power and tools, and understanding potential consequences of actions and, using modeling to predict and things like that. And so, I could be talking a whole lot more about a lot of things around CT, but, I need to stop, but I'm going to say one more thing that I think is crucially important in all of this, and it's this idea of motivation. I've talked about it here and there when I've talked about expansive framing and things like that. But, you have to attend to this intrapersonal piece in the deeper learning puzzle. And we need students to be interested and engaged, and for that you need to connect the learning of all these skills to their personal backgrounds and experiences and interests. Some people actually design their entire curriculum around this, and one example of that is Yasmin Kafai and Debbie Fields' work around e-textiles, where, and also Joanna Good and, UCLA, UPenn are all partners in this NSF work. And they actually have projects which build on complexity and creativity and skill levels. So they have the creative piece very closely intertwined in their project design. And from my own work, I know, they say a picture is worth 1,000 words, and here are 5,000. I've gathered from my many workshops, you see the kids feel so empowered when they're creating and making, and it's hugely motivating for them. And so here are a few things to keep in mind when you're thinking about motivation. President Obama in the US said, don't just play on the phone, program it. And so if you're thinking about integration, we'll say, don't just manipulate science simulations, create them, model them yourself. Don't just use a graphing calculator, program mathematical functions. Use ideas of computational thinking in the wild, bring in culturally responsive pedagogy to the classroom, culturally relevant examples to engage diverse learners. Make sure your examples are relatable to both girls and boys. Encourage creativity for personal agency and lateral thinking for personal expression and such. But also remember that engagement is but one. It's a necessary but insufficient condition for deeper learning. So what we've talked about here are two ideas of CS, of CT. One is a disciplinary thinking skill for CS classrooms, and the other is for integration into non-CS subjects. And I feel some of this confusion comes from the fact that people don't really understand that there are these two views clearly. And whereas in one, you are looking at it as a problem-solving skill, you want to learn to code, you want to learn CT practices, you can do it through coding or unplugged activities, and CT is one end goal of CS. But in integration, you're coding to learn. People talk about, are we learning to code or coding to learn? Well, if you do integration, you're actually programming to learn another subject, to learn another topic. And there you end up using only those relevant aspects of CT that are relevant to that topic. And I've realized this looking at various projects. Not all elements of CT are there in an integration project, but that's okay, because there you're privileging learning of the discipline rather than computational thinking. And there CT is a means to an end. But as part of the K-12 journey, I think students should be getting both As CS is growing as a separate subject, think of it as a disciplinary thinking skill for CS classrooms, and of course, enrich learning in other disciplines through computational thinking. And if you want to go deeper into reading, I've referenced some of these. These are some of the key papers, I think, that deal with just CT in CS, CT in other disciplines. You won't find Papert, Disses, or Weintraub ever talking about computer science as a discipline, whereas Peter Denning, Jeanette Wing, of course, and my articles have all talked about, you know, this thinking like a computer scientist, but also using it to integrate in other disciplines. Now, Jeanette Wing had these very pithy things about computational thinking. You know, it's conceptualizing, not programming. It's ideas, not artifacts. I've corrected them a little bit. I think programming is also CT, so it's conceptualizing, not just programming. She said it's fundamental, not rote. I don't think those are two sides of the same coin. It's a thinking, not rote skill. It's ideas, not just artifacts. Again, not just artifacts. I think artifacts, computational artifacts, can be counted as computational thinking. A way that humans, not computers, think. This is very important. It complements and combines mathematical and engineering thinking. She's right there. She said it's for everyone, everywhere. And people got confused. Are we going to be seeing people doing computational thinking in their everyday life and activities? We've all learned from education that transfer from even one classroom to the next, from one subject to the next, is so hard. I think we can comfortably forget about people trying to do computational thinking in everyday life. I would correct that to say it could happen, but, you know, maybe with time. But I think it's for everyone in every discipline. And I'm going to end with this tweet that Yasmin Kafai tweeted out from the Festival of Learning in London this past summer. It was from the Symposium on Computational Thinking Assessment. And, you know, it was truly a wonderful showcase for the many projects for teaching and learning computational thinking and assessing computational thinking in various settings. And it was clear that people were using CT in different ways for different goals, and their assessment designs sort of mapped to those goals. The plurality of assessments was truly heartening. There was digital ethnographies and portfolios of reflection and scenario-based interviews and online CT assessments. I presented my work, those hexagons there, the systems of assessment, and there was quantitative analytics going on, and examining of computational models and whatnot. And to me, this was as sure a sign as any that the field is truly growing and making progress. We do have a long way to go. I think we are scratching the surface right now, and the road may be bumpy as we try to figure things out, but we're getting there. So, thank you.
Thank you, Shuchi, for such a comprehensive 1 hour talk, but it should be one semester, I think, in this 1 hour. It's all rich, the history of CT, as well as in what way we are going to interpret CT and the pedagogical approach. Okay, it's time for questions, because a lot of collaborators with Shuchi is also in this room, so please. Questions? Rich. Yeah, please.
Yeah, hi. Thanks, Shuchi, for this comprehensive talk. My question is about, the other kinds of disciplinary thinking. You sort of touched upon it, things like design thinking or systems thinking, which are also very fundamental in at least the STEM disciplines. I don't know much about the arts, etc. But how do you see those with respect to computational thinking? Are they complementary, or does one subsume the other? Because I got a feeling that from the talk that CT is sort of covering most of the types of
There
thinking.
are overlaps, you are right. And in fact, just a few minutes before I was having a chat with John Mason, and he was talking about how well in Australia they've been integrating computational thinking and design thinking and systems thinking. He mentioned all of those. there are overlaps, and I think what will end up happening, and as I mentioned, thinking skills, there are bound to be overlaps because it is, certain approaches to problem solving that sort of overlap across these disciplines. I think it's important to know what each one is bringing that is truly unique to that discipline, and I think they are overlapping, so not exactly complementary and not exactly subsuming. But I would say that computational thinking in the act of programming and design and thinking about, it doesn't always happen, but a good computational thinking project could actually be including a lot of those. It does include design thinking, it does include engineering thinking and systems thinking if you're doing, modeling a system and things like that. I think it all ends up being in the context of the project. It may not always happen, but I think it could be that computational thinking ends up subsuming a lot of those. But one could say that if you're just having kids do, say, systems thinking, they are doing several elements of computational thinking, but they may not be doing programming or automating the solution or things like that. So, but it's a good question, and I think some papers, I think the latest one that tried to distinguish between these skills was one by Valerie Shute and Elizabeth Rowe. I think it was called Demystifying Computational Thinking. And about a paragraph or so was dedicated to sort of separating out these, the overlaps and things like that. Yes.
Thank you very much. Thank you very much, Professor Grove. I learned a lot, but still, I have a question in mind. I found that some put STEM plus computational together, but computational thinking together. So I'm thinking, computational thinking is an outcome or skill, right? It's a skill. Can we put the skill with STEM, put them together? Developing,
Yeah. So I think.
So,
go ahead.
I just finished my.
I thought that was the question.
Sorry. So I would like to I want to understand what's the relationship between STEM and the computational thinking. Our computational thinking is a disciplinary knowledge or skill, or
it's a good question, and that is why I feel that it actually that is one way in which it stands apart from all other disciplinary thinking. You don't see scientific thinking being brought into, say, language arts and things like that. But computational thinking is a disciplinary skill for computing, but it's also a skill that enriches other learning in other subjects, which is why I sort of think of it, I don't want to use the phrase cross-cutting. I think that has a different meaning, but it has that, it sort of has that application where it can be taught as part of computer science, but it can also enrich STEM learning. And there you are not thinking about, what does it mean to create abstractions, or what does it mean? It's basically being used in service of the discipline in which it is, being taught, either science or mathematics or whatever. So whenever it becomes the plus C or CT or plus CS or whatever, I think it's sort of being used, like I said, a means to an end. There it's a skill that's helping students. It's a technique to sort of do sense making. Instead of trying to use equations to solve a problem, they're actually designing a model to understand the phenomena and things like that. So there it's being used in service of the discipline. I don't know if I've answered your question, but
thank you for a wonderful presentation. I have to say that I didn't really know much about computational thinking, but have learned a lot about it. Before I ask my question, I want to say that I'm all for computational thinking. I mean, I think it's very important, and it's very important for students in computer science to learn them. But it's also important for people, students in other disciplines or other areas. They also need to learn this. So I'm all for it. I'm not criticizing, okay? So, But also, let me say one more thing about where I'm coming from. So I'm trained as a cognitive psychologist and scientist. So I think it's related field. And initially, when I first started out in learning sciences, I was, for example, taking classes from David Clark when people emphasize scientific thinking skills, which is very close to computational thinking skill. And he did experiment vary one variable at a time, right? There's a name for that and so on. And I think those thinking skills are very much in line with the computational thinking skills. So the part that I wonder, though, is that as a researcher, as I move from along my career, my eyes became open to another kind of methodology, like qualitative research and so on. And I see a lot of this tension between these two methodology, and they are not just about research methodology. I think they're also about how to view the word or try to understand the word. And one thing that I noticed in those tensions, in methodological tensions, is that try to apply those computational thinking or kind of this isolating variables, right? And try to put things in algorithms, or try to come up with some kind of clean representation of the word when the word is very complex. I think that kind of limited our understanding of education or of the word. So I think emphasizing is really fine, but then I wonder, was it always right to apply this kind of vary one variable at a time, for example? The education is very complex, and when
we understand your question because we are running out of time.
Oh, okay,
so let Shuchi have a short answer for you. Thank you.
Okay, so I think wanted to provide some background. So what my question, I guess, is that how can we balance these tensions and help students to learn the skills, but at the same time know when to apply it and also see the complexity?
I think that's terribly useful. And I think that was one of the things that I tried to say, even when you're teaching programming or CT, you want people to understand, you want students to understand what is this skill bringing to the table? When should I be using it? When can a problem be better solved by a human or by a computer? Do we need a program at all for this kind of thing? I think that's actually a very crucial part of the process. So I think I'm glad you brought it up, and I know that comes from deep experience and having seen that in another space. So thank you.
Sorry because we are running out of time, so please talk to Shuchi after this talk. So may I, on behalf of the conference, to present a souvenir to Shuchi for this inspiring talk. So this here come to the end of this section. I hand over the time to Dev. Any logistic arrangement?
Thank you. We are now going to take a coffee break until about 10:30. The sessions will resume at 10:30. Thank you.